Hi everyone, welcome to our project presentation, SensorSynth. For this software, we have multiple tabs, and the first tab is the main page and it's called sensor specification. For demonstration purposes, we have already added a molecule name called arsenic, but for your chases selection and architecture classification, you can select whichever molecule type you want to detect, and the detection threshold, the units of measurement, the output type, whether it can be fluorescence or chemiluminescence, and 5 different options. There is the detection environment, so everything is predefined based on literature, and there is performance requirement section where you can specify the fold change, that is the signal detection change, and the maximum response type for your chases to give the signal. And the main component for this is our host organism and strain selection. There is 6 different chases at the moment, and each chases, when you specify, for example this project, we will choose Bacillus subtilis, and as you can see, once we select the Bacillus subtilis, we are able to visualize the different strains present based on literature analysis, and the specific research focus which the strain can be used for. So I've changed it to sporulation, and once everything is done, you will be able to visually see the specification vector, that is the JSON file, is updated automatically. Once this is done, we can go to the compatibility index, where we will be visually able to see the different scoring systems through which each architecture is classified and the overall score. Once you're able to see this, you can also see that the promoters which are suitable for this system, the regulators, the evolutionary stability, and the explainability. Explainability layer is literature backed up, saying that the specific architecture works for detecting the specific molecule because of the following reasons. So for here, it has dynamic range capability and so on. You can also visually see the full matrix of every single architecture and the organism's suitability, like based on predefined metrics, and every metric is calculated via mathematical simulations and mathematical calculations and formulas. So after this, you can go to this kinetics tab, where you can see the different architectures, the 6 different architectures present in the software, and the different chases you can choose for. And this section is to see how much the ligand concentration you need to give, and the software does Monte Carlo simulations to see how the architecture behaves over time and gives you the ordinary differential equation calculation as well. So once I select the ODE plus MC button, and for the specific MC samples I'm going to run, it will give you the two plots. The first one is the time course, and the second one is the dose response. The dose response is what we need to see for the ligand concentration for our specific fold change, and we can also see the time course, like how the fold change versus time works in a logarithmic fashion. And once this is done, we can also go to the Pareto friend tab. But the thing is, each tab after the compatibility tab is completely unique and different, and they don't depend from the previous tab except for the portability tab alone. So for the Pareto tab, you can visually see that we have totally 36 solutions because of the 6x6 chases and architecture selection. And this tab compares 2 specific features, so one in x-axis, one in y-axis, and we can see what specific trade-offs we get for once we select the specific architecture for a specific chassis. So once I hover over to the star shapes and the circle shapes in this 2 feature comparison, you can see that the TF promoter repressor is suitable for E. coli and the response speed and the low burden. You can also visually see the entire tab as a table below. And after that, we can see the portability layer, where you need 3 specific inputs. One is the architecture you want to move, one is the source chases, and one is the known performance score. This performance score, we can get it from the compatibility layer. And once we give the predict portability across all chassis button, this will lead to all 6 chassis the organisms, and you can see which specific um, that is the given architecture, how well that compatibility is, and the predicted score based on the predicted score we have given for the initial organism and the chassis and the architecture. So after this, you can go to the literature minor, where you can just enter a specific name for your literature. So the name should be specific, because you can see that I'm entering the wrong literature name, and there is no paper mined from this. But once you give it a proper literature name, it can easily mine the specific article and research paper it could find, and it depends upon the number you specify, and it will be able to show you visually that here the Toho switch is present in this paper and they've used it, but the confidence level is 15%, and there are papers which has no abstract and it can't specify the architecture types and so on. You can also use the quick search to see how many papers are available for this. You got 2 papers, and you are able to see that it has a good confidence for the second paper, and they've reported 120 times fold change and the organism they've chosen and the architecture type. So these are all the things, and the last tab is for the stability tab, which is the evolutionary stability and validation. This tab gives you how well the system performs over a period of time, and what is how long it can perform the specific function without degrading or having any problems with signal output and so on. So this gives you an entire metrics tab where you can check the evolutionary stability score with respect to the risk, burden, and the generation and so on. You can also select the validation concordance tab in this section, so that you can see the different chases and how they work for in the different architecture, and everything is given in a clear and simple output. So this project aims to be as a medium layer in between a researcher selecting a project, and they are looking through literature to find the specific chases they want to work with and the architecture they want to choose for their research question. And this could save them time, give them proper validation and scoring metrics for them to compare and analyze, and then finally give them the best chases version and the best architecture possible. Once they are able to figure out the entire overall system, they can easily modify the architecture of the for example, a CRISPR system, and depending upon their own context, they can edit it in different software such as Knox and so on. Thank you.